Finally, we want to take a look at the consequence of the mathematics that we find in the three-dimensional rigid rotor rotational quantum mechanical system. And remember, this is the last slide from the previous slideshow, where we had developed this quantum mechanical wave function for the system that depends on two variables and has two quantum numbers that are defined here. And so we want to take a look at the energy terms for this. Well, beta, we said, was 2 times the moment of inertia times the energy over h bar squared. And we just defined beta from a quantum number standpoint as L times L plus 1. So the energy of this system is going to be h bar squared over 2 times the moment of inertia times quantum number L times quantum number L plus 1. And that defines our energy for the system. So notice that the two-dimensional rigid rotor's energy depended on m sub L and not L, but the three-dimensional rigid rotor's energy depends on L and not m sub L. And we'll talk about why as we develop more and more of the mathematics here. Now let's talk about angular momentum. Just like a particle moving in a straight line has kinetic energy equal to momentum squared over 2 times the mass, we could show mathematically that the energy of a rigid rotor is the square of angular momentum over 2 times the moment of inertia. So we'll call capital script L here the angular momentum. So that means the absolute value of the angular momentum is going to be the square root of L times L plus 1 times h bar, and that means that the angular momentum squared is going to be h bar squared times L plus 1, which means that energy and angular momentum only differ by a factor of a constant, 1 over 2 times the moment of inertia. So L squared and the Hamiltonian operators commute. Now each component of angular momentum is perpendicular to the plane of motion it describes. So L sub x, angular momentum operator for the x-axis, is going to deal with the z and the y-axis, and around the y-axis is going to deal with the x and the z, and around the z-axis is going to deal with the x and the y. And I won't have you by hand convert these to spherical polar coordinates, but the way in which they convert is like this. Angular momentum about the x-axis is negative IH, and then we have the terms that arrives in the derivative terms when shifted to spherical polar coordinates, and then something very similar for the y-axis, but look at for the x-axis. Look at for the z-axis, because the z-axis is the one about which we build the spherical polar coordinate system. It has a much simpler derivative even than the z-axis has in Cartesian coordinates, and that's going to make our math a bit simpler later on. We can go ahead and show mathematically that none of these three operators commute with one another, and in fact their commutators are related to each other. The commutator between the x and the y angular momentum is I h bar times the z angular momentum, and then for y and z it's I h bar times the x, and so on for z and x. Since the components of angular momentum don't commute with one another, the direction of rotation in a quantum mechanical species cannot be specified for rotation in all 3 dimensions. If we know the angular momentum about one particular axis, then we can't know anything about the angular momentum about the other two axes. Now, that angular momentum expression for the z-axis looked pretty special. And so let's try applying that one to our wave function as we've defined it. So we take L sub z, which is defined here, and apply that to the wave function. That means taking the derivative of the wave function with respect to phi, and then multiplying that by negative I h bar. Well, if we're going to do that, then the theta portion of the wave function is a constant. It can be brought out front. And then we take the derivative of this function, and we get the function back, but with plus or minus I m sub L as a coefficient. And so we take that original function, substitute it back in here, multiply this out, and now we have angular momentum is applied to our full wave function is plus or minus m sub L times h times the original wave function. So we have shown here mathematically that the angular momentum operator about the z-axis has our wave function as an eigenfunction, which means around the z-axis is going to commute with energy and with angular momentum, but it still does not commute with y-axis angular momentum or with x-axis angular momentum. So we can know z-axis angular momentum, the square of angular momentum, and the energy of rotation. But we can know all three of those simultaneously, but we cannot know the x and the y along with them. And the question comes up, and I kind of answered this already: why is the z direction special? It's really not, except that what it comes down to is that angular momentum, total angular momentum, energy, and one of the axes of angular momentum are all going to commute with one another. Mathematically, it's going to work out to be whichever axes we build our spherical polar coordinate system around. So if we had built a spherical polar system around the x-axis, then x would have been the special direction. If we'd build it around the y would have been the special direction. But what it comes down to is you can know total angular momentum, you can know total energy, and you can know one angular momentum about one axis all at the same time. But once you know those, you can't know the other two axes. What I've got listed here is the form of the spherical harmonics, what these functions actually look like to satisfy these equations. The first term in each is a normalization factor. Notice that's all that's present when m sub L and L are both 0. The other question that we'll talk about in class is how much space do we have to normalize each of these functions about. Think about that. I want you to think about that on your own, remembering that this is rotation. So how far can it rotate before it has to repeat? And how would each of these functions look plotted? And again, I want you to think about that in terms of how a wave function about rotation would look plotted at different energy levels. The wave functions of the three-dimensional rigid rotor are often written as an orthonormal set of linear combinations. So instead of writing them as the functions that we just listed, they are written as linear combinations of them to eliminate the imaginary parts. And so what comes out of that is functions that will have the shape of a p orbital, functions that will have the shape of p orbitals, in fact, around each axis, and then functions that will have shapes of the 5d orbitals. So this mathematics that we've used to develop rotational quantum mechanical modes is going to lead us to the same kinds of functions when we start looking at electronic quantum mechanics for a particular atom. That's really all I want to say in chapter 7 right now. It might not hurt as you're working through problems and as we're working through problems together in class on this chapter for you to take a look at sections 6, 7, and 8 of the chapter. They're called supplemental or review by the author. We're not going to discuss them explicitly in class, but and I'm not going to test on anything directly from those sections. But if there are things that are unclear in the examples or in the homework, some of the ideas in there may clear them up.